Thank you to the participants of this international encounter with scientific from China, the forum, China Forum on Science and Technology, in this 2025 winter encounter or meeting with China in science and technology. This international meeting of scientists is organized by Peruvian people, Peruvian scientists, with the goal to attract cooperation with Peru in several fields, scientific fields. In this opportunity, this encounter will be moderated by Tadeo Garcia, a Peruvian scientist now investigating, working in China. Thank you, Diego, Dr. Diego Garcia, for this effort. You have to begin this meeting now. Thank you very much.
Okay, my pleasure. I am Diego Antonio Garcia Tadeo, now at Beihang University. I'm here in the campus of Hangzhou. We make the start of the first presentation by Dr. Wang, a building global partnership to advance the new development of space education and capacity building. Doctor can start. Thank you. Thank you.
Okay, thank you, Mr. Chairman. So it's my pleasure to be at this conference, ECI. So my topic is building a global partnership to advance the new development of space education and capacity building. So my name is Wong Jingnong from Beihang University. And also I'm the Dean of International School and the Director of International Relations Department and the Executive Director of the UN Regional Center for Space Science Technology in Asia Pacific, China. So what I would like to share with you 4 parts. So first I would like to discuss the background of the UN program on space applications. So as we know, so 2,000 years ago, the ancient Greek philosophy, he said, man must rise above the earth, then they will fully understand the world in which he lives. So I'm thinking the development of space technology stems from humans' curiosity and imagination. So also we know that in ancient times, people explored the earth by standing on the land. So here I give you 3 scenarios: on the ground, at the seaside, and with a telescope. But now, so in ancient, also the China has a myth, sound, mind's eye, and a long ear. So currently with development of space technology, so all these myths have become into reality. And also, we know space technology, now it can be used everywhere and it can be for everybody. So here, I just give you some landmark in the development of space technology. So the first first artificial satellite, Sputnik 1, is launched into Earth by the Union of Soviet Socialist Republics. And the first manned spacecraft was implemented in 1961. So with the development of space technology, in 1958, the United Nations Office for Outer Space Affairs was initiated, created, and established. So now the headquarters of the UN-USA is in Vienna, Australia. So in order to translate the recommendations of the committee and the General Assembly into an operational program in 1981, the programs on space application, PSA, initiate a project aimed at the establishment of regional centers for space science and technology education at the existing research and higher education institution in each regional covered by the United Nations Economic Commissions, include Africa, Asia and the Pacific, Europe, Latin America, and the Caribbean, and the West Asia. So currently, there are 6 regional centers in the world, include the China Center, India Center, Jordan Center, and in Africa, there are 2, Morocco and Nigeria. In Colombia, in South America and Caribbean, Mexico and Brazil, they are jointly organized one center. So totally, there are 73 countries among the 6 regional centers. So this is a brief introduction about the UN PSA programs. So the second I want to discuss how we have achieved on this framework of UN-USA and the regional center. So from the creation of the program, there are 6 regional centers, and to the global training talents by International Space University. So various high-level international space education and cooperation has been promoted. So here I just show that every year they have an annual report that published in the UN-USA website. So due to time to limit, I just give you an example about our regional center. So regional center for space science technology education in Asia Pacific. So the center established in 2014, November 17. Our mission is promoting the space use of space technology for the benefit of all humankind. The principle of the center is down to us while aiming high. So this is some landmark during the development of the procedure. So currently we have 10 member states. So include Algeria, Argentina, Bangladesh, Bolivia, Brazil, China, Indonesia, Pakistan, and Peru, and Venezuela. So since the establishment, the center has held 6 governing board meetings and 3 advisory committee meetings. So now we offer the degree programs in the following 7 major directions. So include the remote sensing and GIS, satellite communications, global navigation satellite systems, microsatellite technology, space law and policy, space science and environment, space project management. So to date, till now, total near 400 participants have been trained, of which more than 230 have been successfully graduated. Besides the short degree program, so also we organize short training programs in every year. So here I just show you some of them, short-term program. Some program organized in China, some programs we jointly with our partner in different countries, include Tunisia and South Africa, and also Morocco, Nigeria, Brazil, and also Sudan. And also we organize some outreach activities. So one is a poster design concept for China Space Day, and also organize a journey of Chinese space technology culture. So every year we organize our master and buster participants to go into the China space industry companies. So in 2018, so we jointly with other regional centers organized an aerospace exhibition in Vienna to participate in the Unispace Plus 50 activities. And also our regional center closely connected with our industry partners. So here I just have give you a short video for our 5th year anniversary of the center. So last year, so we organized the 10 years anniversary. So, so also more than 300 people attended the events. So include the Deputy Director of UNOSA and the government board members, directors of other regional centers, representative of Chinese government and partners. So, and also we released the Alliance of Regional Center, shaping the future of space education and international cooperation together. And also we established the coordination office for the Alliance of Regional Centers at the Hangzhou International Campus. So during the 10 years anniversary, we also organized a meeting of the directors of all the regional centers. And the forum on international education cooperation, Lunar Research Station, International Space Technology Application Summit, Roundtable Dialogue on International Space Education Development. Also, we organize a campus tour and our center visit for our graduates. So here I just, this is show you some pictures. So currently, so I also introduced Beihang University. So currently we have 3 campuses include 2 cities and 3 campuses. Now we moved our center to our new international campus, which is located in the Hangzhou city. So, which is also a famous city in China. So here I just show you our new campus, international campus. So now the regional center also located in this campus. The third part also, I think, how to establish the partnership of the to advance the new development of UN program on space applications. So in 2017, our regional center proposed to establish the alliance of 4 regional centers, and this proposal also will be agreed by other regional centers and the United Nations Outer Space Office. And also during several meetings to how to promote the alliance. So now we established the framework of the alliance of the regional centers. So here, the 6 regional centers under the umbrella of UNUSA, and also we closely to establish the partnership with universities and the partnership with industry, enterprise. And with this framework, so we are committed to promote the quality space education. So here just list all the member states of each regional centers. And each regional centers, what are the courses, what are the program that can be provided. And also we think that Peru is also our member states. So so we hope Peru can play more important roles in our regional centers. So today also I'm very happy to accept the invitation by our doctor students. His Chinese name is Gao Tian, and English name is Adonio, right? So, and also we also to promote the space education to follow the United Nations Sustainable Development Goals. So, and the goal 4 to promote the quality education. And also we have established a mode, education mode. So for international space education, so we namely is a UGII. So it means our space education hosted by university and supported by Chinese government. And the features of the space education, we closely work with related international organizations and closely work with the industry and enterprise. So this, we think this is our model for promote the education, UGII. And also, I think for each education program, capacity building is a very important part. So also we do some research on the capacity building index. And also we analyze the problems we are facing. So we think there are several problems. So links between needs and the supply are weak, and the training institutions are isolated, and the communications are limited. And there are insufficient development of teaching materials and alternative methods of capacity building are not widely recognized and the lack of fundings. So we think about the education capacity building index framework can be like this. So level one include the teacher team buildings, teaching activities, infrastructure construction, education environment, information dissemination, and funding support. And each level one, they have several evaluation indicates. We think the level second, level two. So for the next step, so we are thinking about to promote the space education. So integrate more resources. So and the more projects include the microsatellite technology, space science, and build an online platform. And also we promote the global partnership, establish the alliance of UN regional centers closely with the institution, industry, and international organizations. So the third, so we think about should the innovation-driven development and to implement extensive consultations, joint contributions, and share the benefits. And also, we are thinking about for the future. So I think we are thinking about it's easy to produce a future if you invent it. And also, I'm thinking space education has bright prospects, and its future depends on our current thinking and actions. So this is my presentation. Thank you for your attentions. Thank you, Mr. Chairman, and thank you, Gao Tian. Thank you.
Thank you so much for the presentation. We have here questions from the people about the presentation. What are the key challenges the center faces in advising space science education, and how do you plan to address them to ensure broader accessibility and impact?
So you mean what's the biggest challenge our the center facing, right? So I think
see.
so I think so we also need to do more so demand analysis. So we notice that different country has different demands, and the participants from different country they have a different background. So how to design to improve our education curriculum or our teaching materials to satisfy the different needs. And also, we should attract more education resources to our center to provide more better capacity building for our participants and give them let them growing much faster. So also we are on the way to do this. Now we are moved to our Hangzhou new campus. So I think we will be upgrade our space education in the future. Thank you.
Okay. Thank you. And other question, this question was in the presentation was mentioned Beihang University. In the history, we know that doctor study at Beihang University. The question is very simple. What is the highlights, in the personal opinion, in Beihang University before the creation of Shahe campus and obviously Hangzhou campus? What are the highlights that remember happy uh, in his study time, Dr. Wang? Yeah.
So what do you mean what is the question to highlight?
Yeah, the times that you remember at Beihang University, in the times of study. Yeah, times that was only the principal campus and the university was growing up. What good reminders about that times can share with us?
So what do the time mean the program duration or something?
About the studies, like for example, in a time that Professor Wang remember that was a high contribution or good partnership between other institutions and was good for the university, a highlight, a good time that Dr. Wang always remember happy is a milestone in the times of Beihang University.
So I'm not understanding your question. What do you mean uh, you mean the Beihang and the center, the relationship or something?
Okay, okay. In the presentation, we can see uh, uh, very clearly the three campus of Beihang University.
Yes.
We
Yeah.
have these three campus, but in the past, before the new campus, the last campus, and Shahe campus, we
Yeah.
have the main campus. Yes.
Yeah.
One highlight is, for example, the creation of Shahe campus. Please can tell us, because the doctor was in that moment that obviously was a high moment, the creation of a new campus. Then this highlight, this high moment, please can give us your principal remind of this obviously happy moment for the develop of Beihang University.
So okay.
Mm,
So
mm,
you know that now the campus have three campus, and
yeah,
all the campus have the different different schools, and also different histories. And for the university side, so they want to uh, use all the campus to extend it, the programs, also the reputations. And the Hangzhou campus is also, Hangzhou is the demonstration of the digital technology in China. So the university side decided to move the regional center from our main campus to Hangzhou campus. So it will be the benefit for the development of the center, I think. So I'm
okay,
not sure if
thank
I
you.
can answer your question.
Mm.
So, uh,
No, no, yeah, obviously it's clear. The technology here even are with a strong. We have close IM group, and yeah, the technology here in the city uh, in the future is a good projection. Yeah, definitely, is clear. Thank you, Dr. Wang. And we have a final question here from the from the people that is writing in the website.
Okay.
Let's see. This last question say, with the rise of commercial space ventures, how does the center plan to integrate private sector innovations into its educational and training programs?
So
I
again,
think this
please.
question, this question is trying to say if the center plan to integrate sectors that are companies, the private sector. I think this is the meaning of this person that make the question. Yes.
Okay. So yes. So I think we because the education in the center, I think should be different with our traditional education program at Beihang University. So is one plan. So we will extend it more to cooperate with industry. And currently, so our professor in the center have signed agreement with the industry. We will establish several joint lab with the companies, and it will be a benefit for our participants to know more about the current the technology, and will be promote our programs, I think.
Thank you. Thank you for that clear explain, Dr. Wang. Then it's finished now, and we say that was a clear presentation, and thank you again.
Welcome. Thank you.
Okay,
Hi,
then
hello.
the next presentation, it's with the title "The Role of Volcanic Eruption in Climate Variability and Predictability." Welcome, Dr. Huo, for the presentation. Thank you.
Hi, hello everyone. I'm not sure which time you. I think good morning, right? Although I'm in close to the
Oh, no.
midnight. Can you
No.
see my screen?
Yeah,
In
it's
the
very clear. It's very clear.
okay. Just give me 1 minute. Make my son away. Here. Now? Okay. Yeah, I would like to give a talk about the volcanic eruptions in climate variability and predictability. Actually, I'm Chinese, but I working in Germany, Guggenheim Center for Ocean Research in Kiel. So if you are interested in any topic about some ocean stuff, I think I'm not expert, but I'm working on the marine meteorology. So that's why I could be talk about the climate variability and predictability. So thank you, give me the chance to give a presentation here. And I think the major reason that I've been invited is that there's many volcanoes in your land, right? I just Google it and surprised that actually most volcanoes are quite active at the moment also. So I would like to introduce a bit, give a brief introduction about the volcano, how the volcano affect on the climate, and what we can take use of these volcanoes for our climate prediction, and how much these volcano eruptions can be contribute to the climate prediction. So it's not just like give only the bad side. We also could take use of these volcano eruptions, get some more information of our futures to do some prediction of about the climate change for near term. So I just like give the first brief introduction about how the climate volcanic eruption affect the climate. Here give a list about time series about all the volcanic eruptions happened in the past and past 200 years, and you can see there's many decrease in the radiation, effective radiation, and until the current. So for every this decrease in the radiation effect basically contributed by the volcanic eruption. For example, Tambora in 1815, and also the Kartora in 1883, and also another one in Pinatubo with quite highest in the record period. And also the latest one is Hanga eruptions in 2022. All these eruptions I highlighted over here is happening in our recent history and also happening in the close to the tropical regions or equator regions. But the Hanga is different from the previous type. Previous, there's a lot of dust and eruptions and bring a lot of sulfate into the stratosphere atmosphere. But for the Hanga, it's a marine volcanic eruption. Volcano, so it brings a lot of water vapor into atmosphere. So the climate effect will be quite different from the others. So I will give more information about this. Yeah, here just the time series about the global mean North Hemisphere on the left side. Time series, the black line, the red line is like contributed by the reconstructed from the observation date, not observation, but the reconstructed date. And the gray line is model simulated, and you can see basically for average temperature decrease, it's corresponding to some volcanic eruptions. For example, even for a group of little ice, even a group of even for little ice, for the beginning of little ice, it may be triggered by a group of volcanic eruptions, and of course combined with some low solar radiations. And the latest one, for example, over here, the some Tamboga eruptions, you can clearly see that temperature decrease compared to no volcano years. And also, if we go back to the like see we care about the historical run from after the industrial period and back to now and forward to now, we could see that there's also some volcanic eruptions, but compared to the global warming, you could see clear temperature increase. Maybe this decrease by the volcanic eruption is not so large. It's even not hard to compare to the trend by the anthropogenic forces by the CO2. But if we look at detail compared to the year, for example, this Pinatubo, compare the year before the volcanic eruption, it's definitely cooling the surface, right? So I will give more more slide about the mechanism, how the volcano effect on climate. And here give an interesting photo that from the Earth sunset for the Pinatubo eruption. This figure is before the Pinatubo eruption. You can see clearly conditions for the air atmosphere. But after the Pinatubo eruption, you could see two dark layers of aerosol mark distinct boundary condition for the atmosphere. So this basically is the aerosol layers around 20 to 25 kilometers. This is due to the volcanic eruption for the Pinatubo. And also what is delivered to the atmosphere during this Pinatubo type eruptions is of course a lot of air, also a lot of gases, include water vapor. Basically, it's covered 50 to 90%. Also the CO2, also the sulfate gases, and also another cyclone and bovine other gases. The highlight over here is the sulfate gases. It's not so the a company is not so large, but it like from 1 to 35% compared to water vapor is not so large, but it might lasted a longer time in the atmosphere condition and also change into the sulfate aerosols and then influence the climate conditions in later years. For example, here give a structure about how the volcanic eruptions influence climate. For example, the first step, of course, the eruptions bring a lot of aerosols, as and also a lot of sulfate into the atmosphere. Basically, it's into the stratosphere, lower stratosphere, and even higher stratosphere. And then that's about the layer above the troposphere, and this sulfate aerosols will be like the SO2 will be interactive with the other water vapor, and also due to the radiation from the solar, and then it will change into a sulfate aerosol. And this sulfate aerosol in the stratosphere is quite hard to remove, but of course it could be partly removed by some processes, but most time they maintain a little bit more longer than 1 year, and then the impact the hydrochemistry will be increase the planet enthalpy and lead to a warming in the stratosphere, and also cooling at the surface. And also, of course, this aerosols, sulfate aerosol will be removed by the precipitation, but before they be removed, they will influence the precipitation also. So if change the precipitation, definitely influence the surface, the river runoff, also impact the vegetation. So some side effect also due to this volcanic eruptions. And basically this can could, for example, the Pinatubo, it can cause the Earth by cooling 0.5% for 1 year, and most like a major eruption in the historical record, it could reflect sunlight, cause global cooling around 1 to 2 years. For example, here is the time series for the temperature anomalies. You can see that in this siltstone eruptions and the Pinatubo eruptions, the stratosphere gets warming due to the sulfate aerosol, and then we could say that at the surface the temperature decrease after the volcanic eruptions. It's not just immediately happen decrease and last for around 1 or 2 years. So this gives us some feeling that for the volcanic eruptions, if they has a lot of sulfate aerosols into the stratosphere, it gets surface cooling, stratosphere warming. But there is special cases for the eruptions. That's a Hong Kong eruption. It brings a lot of water vapor into the stratosphere. It's really high top. It's reached the stratosphere stratopause. So it's really high top eruptions, and from the underwater, so it brings a lot of water vapor into the stratosphere, and this will be definitely caused the stratosphere cooling. You can see in 2022, compare the previous years, there is extremely stratosphere cooling effect. So for the water vapor, for the Hong Kong eruptions, it's quite a new case that is totally different from the previous ones. There's very little minimum aerosol formation, and no, because there's not very little SO2, so no significant cooling can be expected. But instead, it eject a lot of water vapor into the stratosphere. So basically, it could be like account 8% for the total water vapor in stratosphere. So it will increase the infrared radiation trapping, cause the surface warming. So it's opposite to the, not totally opposite, but it's different mechanism from the sulfate aerosols. Here give a lifetime to show why these volcanic eruptions or the sulfate aerosols in stratosphere can last for a longer time, and why it can cause such a surface cooling or warming effect. You could see this lifetime for stratosphere aerosol, and basically this one is shows the observation date that from the Glosas Saska and after the Pinatubo eruption. In the first months after the volcanic eruptions, you can see that it's happening in the tropical eruptions. It's happening the aerosols into the stratosphere, lower stratosphere in the tropical regions, and then it's a little bit after 2 months, 3 months later, and it extends into higher, and also you could see it transpond into the polar region by meridional circulations in the stratosphere, and also you could see that quite large extension, and also even get a maximum after in the polar region in 1 year later. This extension or transpond into the polar region will be influence the ozone formation. It will influence the ozone distribution in the polar region. Sometimes causes the extreme ozone hole over the polar regions for some cases. And basically after 2 years, it's just is decreased, the aerosols it will be decreased, and also basically 4 years it disappear, very lower mass density in the lower stratosphere already. So basically the effect for the climate, the aerosol effect on the climate could be last for maximum is 2 years for the Pinatubo. And also here example for the Hong Kong token eruption in the record, it is ECMWF and AFS is total SO2 is happening over here, the eruption, and at that time in January 16, and like basically 5 days later, it transplanted eastward, transplanted to the westward and dispersed. So basically, the climate effect is not only limited to the location where the volcanic eruption happened, but also in other regions, because the aerosols or the masses is from the eruptions could be bring or separate spread into other locations after a few weeks or few months and even a few years. Yeah. So basically here I will give a summarize about the volcanism effect on climate. They directly affect the surface of the Earth's radiation balance, and thus it will be alter the surface temperature, and they will introduce a horizontal and vertical heating gradient, so they can alter the stratosphere circulation into affect the troposphere. For example, the volcanic eruptions will be increased temperature in the stratosphere, and for here, so in the red color, and then this increase in the meridional. Maybe I could say there's a puncture itself. Yeah, they will be increased meridional temperature gradient due to the thermal wind balance. We could see a stronger polar vortex over here, right? So that's the effect in the climate in the stratosphere, but also this polar vortex increase will be some positive phase for the North Atlantic oscillation. So also effect on the surface, and also the surface cooling, of course. And also they can interact with the internal climate mode. For example, the ENSO, the North Atlantic oscillation, the QBO, the quasi-biogenic oscillation in the stratosphere, and also some dynamic noise. So they could be triggering or amplifying or shifting these modes. So sometimes maybe before the volcanic eruption or no volcanic years, NO is negative phase, but when the volcanic eruption happens, the polar vortex will be triggered and will project into the North Atlantic region, will be triggered positive phase for the NO. So this interaction makes the effect is more complicated. And this volcanic eruptions for the aerosols will be provide surface for the chemically affecting for the global stratosphere ozone. I mentioned there maybe when the aerosols transplanted into the polar region, it maybe dissipates, may be lead to the ozone depletion, so bigger ozone hole, and also, of course, they will be perturbing other trace gases. So how we can take use of this effect from the volcanic eruption for our climate prediction? Because when we do prediction, we normally, for example, when we check our cell phone for the weather forecast, we could see for 1 week or for 10 days, right? But normally in 2 hours and 3 hours is perfect. But for like 12 hours or 40 hours, 24 hours, it's already not that accurate. And also this table shows that how much we could trust it, and basically after 1 week, it's hard to give accurate weather forecast. It's hard 50-50, half. So it's 50%, just like we could be asked ask a 3 years old kid to ask about what happened on next week. Even like the same result we could get for the weather forecast. So it's not accurate anymore for after 1 week. And if we're considering the contribution to this weather forecast accurate, and basically for the weather forecast for the very short time, for example, in 12 hours, it's controlled for the quality for the weather forecast. It's really controlled or based on the no casting. So based on the data we have at the moment for the 12-hour forecast. But after the 12 hour, for the 24 hour or 34 hour, 2 days later and 3 days later. And it's not just depend on the initial condition, we would say, or no forecasting date. It's also based on the numerical weather prediction. This weather prediction is not only the initial condition, but we also need the boundary condition. That means external forces, not only the climate system itself. It also we need the boundary condition, for example, the solar variability, for example, the volcanic eruption, the change in CO2, any other external forces. So that's the difference between the weather and the climate forecast. Basically, for the weather forecast, it's just a very short-term change in atmosphere, so it can be changed from minute to minute, hour to hour, and day to day. But for climate forecast, normally we describe the average weather conditions in a specific area over a long-term period, for example, 30 years. Normally, we could do sub-seasonal to seasonal forecast, seasonal to decade forecast, and even 30 years and even more for the weather prediction. So as I mentioned that for weather forecast, basically the quality for the weather forecast controlled by the initial condition, and it's decreased when the forecast time increased. For example, from hours it's perfect, but from day to week it's decreased. The quality is decreased. And also for the year's prediction or sub-seasonal to year's prediction or for decadal prediction, basically controlled by the boundary condition. So that means that if we give a more correct boundary condition, we could expect better prediction climate prediction for next season. So that's the definition for what's the climate weather condition forecast, what's the climate projection. Climate prediction and climate projection. For climate prediction, we still need the boundary condition, initial condition from week to several years. But for climate projection, we basically do the projection for the very long-term run to the end of 21st and 21st centuries, and based on different scenario about the future society development. Normally, we describe the greenhouse gases or describe the anthropogenic forces. Yeah, that's we could get some predictabilities from initial conditions for weather forecast. We also could get some predictability right from the boundary condition. You could see that this blue lines, so is from different initial conditions with a multiple model, basically decrease quite fast. Basically, after 3 years, it's hard to get some prediction scale. And for weather, for the prediction from the border for the climate prediction, actually it's not bad. It's not so good in the few years. After the decadal prediction, it's more better. So basically 30 years, it will be more easier for us to do some weather prediction. It depends on the boundary condition and depends on the climate system. This structure shows the sources for the near-term prediction. Predictability, basically you could see the solar variability and changing ozone and also atmospheric chemistry, also pathogenic forces in aerosol, greenhouse gases, and also changing in the volcanic eruptions. It's related to the volcanic aerosols. It's the major, also very important potential contribution to the predictability. And of course, also there's many other climate modes, for example, the unsolved meridional circulation, and also the QBO, and also Fitkind, and also sea ice, changing sea ice, snow, land. But except among of them, actually, the boundary condition is more important. For other, the red circle, so is the initial condition. Yeah, and also for the volcano aerosols, actually we not only care about that in the weather forecast, we more care about in the climate prediction. So it's basically from month to season, or even annual, decadal, multi-decadal. And basically the volcano aerosol is contributed to the seasonal to annual because the effect for the aerosols lasts for 1 to 2 years. And also we could see that also from time scale and also from the variance. So the variance is not only this volcano aerosols is not just the boundary condition for the stratisphere. actually, for the troposphere, actually, we need to know the volcanic aerosols distribution in the stratosphere, what it looks like. Yeah, here give a simple model for the Lorentz model to understand why we could do climate prediction or weather forecast and what's happened if we add external forces to this system. Basically, the prediction system state at some future snapshot in time. For example, at the moment we are at the T1, time 1, and for future we want to know what happened to T2. So after the time step of that T, we know without external forcing. So we will change the boundary conditions. We will see that the green line is no, the black line and so circle shows no boundary conditions, so no external forcing. The green line shows added external forcing of 10. We could see clearly that there's more like distribution or tendency for this distribution. If we plotted PDF, we could see if there's no external forces, it's just normalized distribution. But if there is a boundary condition or external forces, the distribution have a tendency to the right side, right? So that's what happened, right? We need a boundary condition. They give us that the more tendency of what happened in the future snapshot. So the boundary condition problem basically is the predictability of the second kind. And here is still the Lorentz model. You could see we described variables at time t. We could know what happened in the future, but you see that for the predictability, it's just the distribution is normalized, and we could know some weather region over here. This one is predictable. But if we have a external forcing, for example, we added aerosol from the volcanic eruptions as a boundary conditions, we could see that there's more weather regimens distributed in the right side or in the positive values. So that means at the external forcings at the boundary condition for example volcanic eruptions, we could get more correct or accurate for the prediction because there is more clear distribution and more clear tendency and more clear weather distribution, right, in the system. So that means that if we have a really good climate model or climate system or climate model to simulate the system or weather forecast system with added external forcings, we could expect a better prediction skill. What we need for simulated volcanic eruptions. Here, I just give a structure about the Earth system. It's quite complicated, right? And for volcanic eruptions happen over here, it erupts a lot of gases and particles. It will be transported by dynamical circulations and interactive with some atmospheric chemistry, other trace gases, and so we need the chemical interactions, describe the circulations. A lot of processes need to be described in the Earth's climate system. We need to describe the system in such a different horizontal and vertical grid. And some physical processes in the climate model cannot describe because this grid is too big for small regions. Some small process cannot capture by this grid. So that means that we need to pre-describe or parameterize some process. But at the moment, where our climate model already developed very, very fast and very good state. For example, at the beginning, we only have atmosphere, land, ocean, but they can couple to each other and include the sea ice. And now we could include the sulfate aerosol, dust, carbon aerosols, interactive vegans, and the carbon cycle. And then in recent decades, we could include the upper atmosphere. That means that you include the stratosphere also, and also include the atmospheric chemistry. That's really important for simulated volcanic eruptions because most important process or effect happen in the stratosphere. That we need the upper atmosphere component. And also need the atmospheric chemistry to know how the SO2 formatted into the sulfate aerosol in the stratosphere. So can climate simulate the volcanic signals? My answer is yes. Climate model already have radiation code to calculate the extinctions, how to scattering and absorb the eruptions in the atmosphere layers due to some chemical companies. And also this implement the aerosols to be easy as long as we know the radiation properties of the aerosols. And basically stratified sulfate aerosols are well promised as a sulfate particles mean based on mean survey can be used in predictive reactive process. So that means that the climate model can be able to capture the volcanic eruptions. For example, here the effective radiation forces due to volcanic eruptions marked over here Krakatoa and also different Pinatubo, different volcanic eruptions. And then we can see clearly there's anomaly for the surface temperature from the different climate models. There's definitely a response to these volcanic eruptions. Here, this one. So the model able to capture the capture the volcanic signals. Although maybe for different ensemble members could be different, and the model also could be different, but basically in general, all the models could capture the signals. And this figure shows in the prediction system. The climate model is okay, and for the prediction system, what happened? This figure shows this left on the side, left side is the result from climate from the prediction system, and the right side is from the observation date. And this on the left side is average over all three volcano eruptions. And you can see the warming in the stratosphere is well captured by the climate model, and also a bit like in the winter season the increased or stressed the polar vortex also can be simulated in the climate model. But compared to the observation, it seems like the response in the dynamical response in the polar vortex is a bit weaker than observed. And also basically in the 2 years after, in the second winter, after the volcanic eruptions, in observation we still can have a structured stressed polar vortex into the troposphere even, but the model cannot. So there's still some different the model still not the prediction system not perfectly capture the prediction capture the effect from the climate from the volcanic eruptions. But this prediction means that but the results still could be so as that after volcanic eruptions, the climate system at the volcanic eruptions we could know what happened after in the winter after eruptions. So also this one, for example, in the climate model, we also could see at the surface there's positive unknown phase in the first winter after the eruption, and also in the second winter after eruptions. Basically consistent with the observation for the first winter, but it's totally different for the second winter. So it's still limited to the 1 year after the eruptions for this prediction system. And also there's another cases for the Pinatubo eruption. For example, the eruption happened over here, and the 2 years later, and also how it transponded into the polar region, and we could see what happened in the surface. We could see in 2021 and 2024, it's different phases for the climate mode for the Pacific Decade Oscillation and the North Atlantic Oscillation. If both of them are in negative phase, we could see for the lead 1 or 2, 4 years. So that means 1 and 4 years after volcanic eruption, we could have a surface cooling. And after 7 years and for decade prediction, the surface cooling, the scale of our surface cooling is not so clear. But for the 1 to 4 years, clear surface cooling prediction. And also it's different phases. If it's two major climate mode in positive phase, the effect is a little bit different from the negative phase. It's more cooling in the polar region in the positive phase. So the difference between these two could show some interaction between the internal variability and this volcanic eruptions. Basically, they could get some positive effect actually in the polar region. So if we want to correct prediction based on the volcanic eruptions, the initial condition for the climate forecast is how to initialize. It's also related to the climate mode, of course. It's really important, and also how we view distribution for the volcanic eruption in the stratosphere. It's really carefully give a correct distribution for the stratosphere aerosols in the stratosphere regions in the climate system, also important for our prediction skill. For example, here give another prediction, another example for the prediction. Volcanic force list over here include this 5 major eruptions, basically 3 major eruptions and 2 small eruptions, and this forecast system for the decade for 6 to 10 years with volcanic eruptions and without with no volcanic eruptions. An interesting part is that actually with volcanic eruptions get us high prediction skill in the West Pacific region, in the tropical region, and but without volcanic eruption, we get high prediction skill in the tropical, in the Central or the East Pacific. So basically, volcanic force in sometimes it depends on which location you are looking at. The volcanic force at the volcanic force sometimes could decrease the multiple to decadal prediction skill in the tropical Pacific regions. For example, here, into the volcanic eruption is decrease the prediction skill. So it's really need to be more studies about this, how we can involve the volcanic eruption in the system, how we can take use of this to get increased prediction for our weather forecast from multiple years to decade. Okay, here are my take-home message. Basically, I introduce the volcanism effect on climate. If it's pinatopo type, that is not from the marine volcanic eruptions, it's from land. And then it could be bring a lot of aerosols or a lot of ice and SO2 into the stratosphere. They also change into the sulfate aerosols to last longer, like 1 or 2 years in stratosphere before they be washed off. So it will have some climate effect, warming in the stratosphere and cooling at the surface. The special cases is for the Hong Kong type eruptions because it's a marine meteorologist from water, from the under the water, then bring a lot of water vapor into the stratosphere. This will be like includes the decrease the temperature because it's limited trapping the more long wave radiation to space. So will be cooling the stratosphere and warming the surface, slightly warming the surface, of course. And also very limited aerosols in SO2 in this marine volcanic eruption. So the effect on the stratosphere or the warming in the stratosphere is very small, hard to expect. And for the near-term climate prediction, if we take use of the volcanic eruption into the near-term climate prediction into the prediction system, we could expect that there's more prediction skills from multiple years to decade from the volcanic eruptions. For example, with the volcanic eruptions after the Pinatubo eruptions in 2 years, the aerosols distributed into the polar regions. We could have clearly could forecast predict for the next 4 years a cooling at the surface and also even for a decade. Okay, that's all. Thank you for your attention. And if I still have time, I'm happy to answer your questions.
Thank you so much for that interesting presentation. And here we have a question from the people. What are the case challenge in incorporating volcanic forcing into their climate prediction models?
For the challenge?
Mm-hmm.
Yeah,
What are the
actually,
key challenges? Mm-hmm.
yeah, the key challenge, I think it's the process that how we could accurately prescribe the stratified process. For example, the meridional circulation, because it plays a role for the distribution for the surface errors in the stratifier. And normally we still have a lot of bias in stratifier. And another case process is the chemistry in the process because it's basically could be interactive with the SO2 and all the other trace gases into the stratifier. If it's pre-described in the stratifier, that will be like a bit at the moment. Most prediction system pre-described the response into response to the stratifier to the volcanic eruptions in the stratifiers. But if we have an interactive chemistry in the stratifier, it will be make more like not reasonable but more close to the real system, real climate system, or real Earth system. So that's still quite challenging because the process is sometimes hard to prescribe, hard to give a capture by the model itself. Sometimes we still need to parameterize, and also the different process how to will be really increase the computing costed. So it's if for include interchemistry, it will be very, very expensive.
Okay, then other question here. Why do some major eruptions lead to detectable surface cooling, while others show minimal thermal effects despite significant stratospheric water vapor injection?
Could you please repeat the question again? I'm not sure I
Sure,
get the
sure, no
point.
problem. Why do some major eruptions lead to detectable surface cooling, while others show minimal thermal effects despite significant stratospheric water vapor injection?
I think maybe I repeated the question. That means why it lead to a surface cooling, right? And then, but some with the water vapor, it will be a bit slight warming. Is that right? The question is.
This question is, I think the person that make this is that we have two different scenarios, right? Then
Yes,
one is
different cases.
detectable. Yeah, one is detectable and another one is not detectable. Then, in a simple question, why occur these effects? Yeah, yeah.
How it's detectable? It depends on how much the or the index, not the index, but the how large or how big the eruptions itself. And also, of course, it depends on the location, of course, the season. Normally, if the volcanic eruptions happen in different location or different latitude, for example, happen in the tropical region, it's if this really eruption is really high top, it's into the transfer, it will be transformed into the polar region or dispersed into the polar in the global view. So it will be have more climate effect and more clearly surface cooling effect. If this binary type, that means that more surface SO2 erupt a lot of SO2 into the transfer. But if it's volcanic eruption is not happen in the tropical regions, it's more happen in the high latitude. For example, the 40 north degree or 50 north degree happen in summer season, it will be has less effect because before it dispersed into the or not reach into the high top, not reach into the stratosphere, only limited into the troposphere, it will be washed out by the precipitation quite soon. So just a few days later on, basically most of the ice and most of the SO2 will be washed out. So cannot disperse into the global into other locations, cannot have a global effect or cooling effect for surface. That's for the second one that it cannot be detected because it's not has such a long. It only can only when the aerosols or SO2 into the stratosphere, it can be maintained longer, stayed there longer, and distribute into other directions. But for the if it's not reached into the stratosphere, only in the troposphere, it will be because the dynamical process in the troposphere is very fast, and there's a lot of like the water drop, a lot of precipitation. So the aerosols as will be washed out quite soon. There's not so like not last for 1 year, maybe just a few weeks later on, there's no effect anymore. So for this cases, for these eruptions, it's hard to detect any effect on climate because climate normally we look at the state quite for long term, right? But this effect, for example, the short term volcanic eruptions, even in not enriched in the stratosphere, only in the troposphere, we still could affect that influence in the regional weather. on climate, not climate, but regional weather.
Thank you.
I hope I get the
Yeah,
point
yeah.
and clearly answer the question.
Yeah, definitely. The study zone takes a crucial role here. Thank you. Thank you.
It's my pleasure.
Then the next presentation has the title Near Real-Time Monitoring of Anthropogenic Carbon. We will see this great presentation now, and I suggest variation since previously I watch this presentation and it's so good and very informative. Thank you so much.
Thank you for introduction. Let me share my screen. I have sent a request for sharing the screen. Can you see my screen now?
It's clear. Yeah.
Okay, thank you. Okay, hi everyone. I am Xinyu Dou. I'm currently a energy fellow at Stanford. And this time I'm very excited to share our work about the near real-time monitoring of anthropogenic carbon emissions. Greenhouse gases, also known as GHGs, are gases in the Earth's atmosphere that trap heat. Anthropogenic greenhouse gases have contributed about 1.5 degree of global warming since the industrial era began around 1850. And CO2 contributes 0.8 degree to current warming. Among all greenhouse gases, CO2 is the largest contributors to global warming, outpacing methane and other gases. And the NAVA's Global Greenhouse Gas Reference Network observed that the atmospheric concentration of CO2 continues to rise. And the main reason for the increase of concentration in the atmosphere is the rising emissions caused by human activities. Human activities have caused a large amount of emissions, especially after 1950, due to the large-scale fossil fuel use. For CO2, anthropogenic emissions are from the consumption of fossil fuel and industrial process. And in the face of the so severe climate change, accurately quantifying anthropogenic CO2 emission is very important. In this field, in the field of quantifying carbon emissions, we faced with a core scientific issue, that is, how to quantify the true value of emissions. Unlike the atmospheric concentration that can be directly measured by instruments, emissions cannot be directly measured by physical means. It requires the integration of investigation, measurement, simulation, statistics, and other aspects. And in short, there are two main approaches that can be used to quantify carbon emissions. One is top-down emission inversion. It means estimating emissions based on observed concentrations and atmospheric transport models. And another method is bottom-up inventory model. It is a kind of a statistical calculation. It uses activity data and emission factor to quantify the emissions from specific sector. Each method has its strengths and limitation. Before introducing these two quantification methods, let's first move to the characteristics of CO2. Carbon dioxide is a long-life gas, has a high background concentration in the atmosphere, and it is easily transported by meteorological factors. As a result, anthropogenic measurements cannot directly reflect actual emissions. Moreover, anthropogenic carbon emissions come from a wide range of sources and has one wide distribution. So it is difficult to conduct large-scale and continuous monitoring. For the quantification methods in detail, for the top-down method, and atmospheric observations provide relatively accurate spatial distribution data for gas in the atmosphere. Especially with satellite observations, we can monitor emissions in hotspots. However, for CO2, the current carbon satellite observation samples are still very limited to local areas, such as power plants or big cities. So it is difficult to quantify global CO2 emissions using this top-down approach. And also, there are large uncertainties in the measuring instrument and inversion models themselves. Another method, bottom-up accounting method, can distinguish and quantify the specific emission source. Using the inventory method, the emissions from fossil fuel use and industrial processes can be accounted for with relatively low uncertainty. This is because the inventory method is based on the principle of material balance, and the whole calculation method and parameters used are relatively simple. And the energy statistics are generally collected by national statistical agencies, and emission factors can be determined experimentally. So as a result, the overall uncertainty is relatively controllable. This method has been compiled into an accounting guide by the IPCC and provided to various countries for accounting. Well, there are still some limitations for this approach. This is since the energy statistics are traditionally used as activity data to calculate inventory. So the accounting results are limited to annual resolution and has a time lag of over 1 year. So this is and there is a urgent need for near real-time carbon emission monitoring across governments, societies, and companies. At the government level, near real-time monitoring enables timely assessment of the impact of climate mitigation policies and measures implement in different regions. And it also allows for tracking process toward targets such as carbon neutrality and carbon emissions peak. And moreover, near real-time emission data can offer more timely inputs for forecasting future emission trends, enabling more accurate and scientific assessments of how difficult it will be to achieve temperature control targets. And at the society and the company levels, the operation of carbon trading markets also depends on timely emission monitoring to provide a scientific basis for transactions. And a critical issue in the current field of carbon emission monitoring is that traditional emission data are significantly delayed. As a result, actions and policies often rely on historical rather than timely data. This is like a driver standing on a highway who can only see what's behind through the renew mirror, relying on past data. When an unexpected event occurs, such as a deer suddenly appearing on the road, the driver is unable to react in time to brake. This is a dangerous driving for any individual, and similarly dangerous for all the humanity in the face of climate crisis. So under this background, our work focuses on accurate and timely anthropogenic carbon emissions accounting, building on the bottom-up approach mentioned above, and enhancing the traditional methodologies. For the current research gaps of this field, one is that data updates have lagged. Recently, advancements in technologies such as multiple observation, like remote sensing, offer an opportunity for us to achieve the near real time. Beyond the timeliness, existing research mainly offers annual quantification. And some studies have improved the daily estimates at the national level, but cannot keep updating. And also, there is still a challenge in achieving both high spatial and temporal resolution. So our focus is on achieving near real time and high resolution accounting for anthropogenic carbon emissions. In our research, we near real time monitor anthropogenic CO2 emissions, including multiple sectors like from transport, power plants, residential consumption, industry, and so on. By using such improved IPCC bottom-up inventory accounting model, we employ near real-time human activity data to estimate emissions instead of using the traditional energy statistics with high latency. And by integrating sectoral human activity data, such as power generation, traffic congestion index, real-time flight data, temperature data, and so on, we calculated near real-time daily sectoral CO2 emissions at the national level, called Carbon Monitor. Carbon Monitor calculated near real-time daily national CO2 emissions in 7 sectors, including industry, power, residential consumption, ground transport, domestic aviation, international aviation, and international shipping. Carbon Monitor improves the timeliness from a lag of more than 1 year to near real time with only 1 month delay, and improves the temporal resolution from the original annual change to the daily resolution. So we can see the seasonal pattern based on our Carbon Monitor dataset. And in order to improve the spatial resolution, we use global monthly spatial patterns of CO2 emissions to downscale national CO2 emissions to grid level. For large countries being major emitters, we further employ a subnational proxy according to NO2 concentration retrieved from Troponomy to distribute national level total CO2 emissions into subnational totals, followed by a 0.1 degree downscaling according to the spatial patterns. And the detailed method framework is shown here. It uses spatial patterns from EDIGA as well as a subnational proxy according to Troponomy NO2 retrievals in order to distribute Carbon Monitor daily emissions at national level to our final grid. And this is a summary of our overall methodology framework. At present, we have developed these results into publicly accessible data platforms offering free downloads. This include the carbon monitor, the global near real-time national level carbon emissions database, and GRIST, the global near real-time graded CO2 emissions map database. Next, I will introduce the results we got and share the key patterns and insights derived from them. Okay, so for the results, we provided GRIST, the first near real-time global graded daily CO2 emissions dataset. GRIST can be updated in near real time with a spatial resolution of 0.1 degree and a temporal resolution of 1 day. In addition, GRIST can further focus on the provincial or even urban level in space, so as to more effectively support the realization of local climate mitigation goals. Such timely and high-resolution datasets can reveal patterns that were previously not captured by traditional data sources. For example, we are familiar with the seasonal variation of atmospheric CO2 concentrations. Generally, the pattern is generally lower in summer and higher in winter. This is because plants absorb more CO2 during the growing season in summer. It should be noted that the winter we are talking about here is the winter in the northern hemisphere, where most of the population lives. And the overall upward trend reflects the large amount of CO2 emitted by human activities. But currently, what we didn't know before is that CO2 emissions from human activities themselves also have clear seasonal patterns. Emissions are typically higher in winter due to heating demands, and also relatively high in summer due to cooling needs. In contrast, spring and autumn has lower emissions. In addition, we can clearly observe a variation pattern in the data. This reflects weekly fluctuations in human activity. Emissions are higher on weekdays due to work-related activities, and lower on weekends due to reduced activity. And by at this figure shown by comparing 2020 and with 2019, we can see a significant drop in emissions in February 2020, which reflects the impact of the COVID-19 pandemic. Well, traditional data sources were too delayed to reveal this trend. Our carbon monitor dataset makes it possible to clearly observe the global CO2 reduction during the pandemic period. And near real-time data also reveals the most recent changes in anthropogenic carbon emissions. It allows for timely evaluation of emission pathways. Although global CO2 emissions dropped sharply in 2020, they rebounded significantly in 2021. And based on the current data estimates, global emissions are still on an upward trend. This increasing trend is actually inconsistent with the emission pathways required to meet the 1.5 degree and 2 degree temperature targets set by the IPCC, which assumed that global emissions would peak before 2025. And in light of these recent changes, we have also updated the estimates of remaining global carbon budget under the Paris Agreement temperature goals. If current emission levels continue, the world will exhaust the entire remaining carbon budget within the next decade. Therefore, urgent action on climate mitigation is more necessary than ever. This dataset emphasizes near real-time capability. Its update frequency and release speed are higher than those of other databases. And a critical question here is how to verify the accuracy of this dataset. And for grid level data, uncertainty analysis gives a grid level 2 sigma uncertainty value of 19.9% generally. It can be acceptable in this field. It indicates the reliability of GRIST was not sacrificed for the sake of higher spatial temporal resolution that GRIST provides. And the comparison with other similar data sets also shows that the similarity in emission distribution and the number of non-zero emission grids among them, which represents GRIST has been verified to some extent. And at the global level, we also compared our data with other data sets. This figure shows a comparison with other annual inventory results. As this figure shown, our data aligns well with those from IEA and GCP. And this figure shows the comparison with other daily results, also aligns well. However, such a data set like cannot be updated for a long time after the pandemic. So Carbon Monitor is the only one daily CO2 emissions data set that can be continuous updating now. And in terms of data availability, we established search visualization and download website. Here are a few videos. The highlight of this website is that you can see the changes over time with a timeline at the bottom of this website. And furthermore, you can filter the date, the sector, and regions you are interested in for display. We hope by establishing such a website can support researchers, institutions, or governments in need. And Carbon Monitor is a project contributed by more than 30 international research institutions. We developed and published a series of datasets at different levels, and they have been downloaded over 1 million times. Like for we have different levels datasets like grid level, like the national level, and the provincial level for China, and the individual country level for Europe, the state level data for US, and even cities level. Because for different sectors, the resolution is various. For some sector like power sector, we can even provide not only daily data, but also hourly level data. And this data set has been cited in the national report at the United Nations SDG Summit. It has also been cited by the IPCC Global Carbon Budget as foundational data. And furthermore, this data set also was reported on the keynote speech at COP28. There are relevant publications about our work. In summary, this research holds exciting potential for the future. The first one is near real-time data on energy-related carbon emissions reflect how people use energy. For example, analyzing the near real-time data will help us understand when, where, and how people consume energy. This information can guide adjustments to the use of energy sources, making energy use more efficient. And the second one is near real-time data reveals the latest emission trends. It allows us to redefine the global GHG budget cut down, like this figure shown. And the third one is this grid level monitoring can also contribute to energy transition at even single infrastructure level, and can help like this framework for monitoring other gases like methane emissions can also contribute to detecting the emissions from methane links of ultra emitters quickly. And looking ahead to the future of carbon emissions monitoring, as satellite technology continues to develop and the establishment of satellite networks, integration of top-down hotspots observations and bottom-up near real-time data and integrated monitoring system can be expected to become a key and promising developed direction in the field of quantifying the greenhouse gas emissions. That's all for my sharing today. Thank you so much for your attention, and I'm open to any questions and discussion.
Thank you for the great presentation. Here we have a question. Which sectors are easy and hard to track in real time?
Okay, thanks for your question. So I can change to the method framework of our work. Like for the aviation and shipping sector, it is more easy to track the near real-time pattern based on some international database compared to other sectors. For the power sector, it is more difficult to track the near real-time pattern because there is not a public international database that can provide the power generation for all countries. So we have to collect the data for individual countries independently, like for the US, we can collect the data from the official energy website of the US, but for China, it is difficult to find. So we have some cooperation with the government in China to get the power generation data. So for this sector, it is generally more difficult to collect such near real-time activity data.
Okay, thank you for the clear explain about that. This was a great presentation, and the next it's titled Evaluation and Optimization of Road Network Resilience under Urban Rainstorm Scenarios. Thank you.
Hello? Can you hear me?
Very clear.
Okay. So let me share my screen. All right. Can you see my screen?
Yes, very clear. Thank you.
Okay. Thank you, Dr. Antonio, for the invitation. And today we hear very variety of presentations. My name is Jing Ran from Hunan University in China. My research interest focus on the flooding modeling and any research related to flooding. Today, I'm going to share a small research that we have done recently, which is evaluation and optimization of road network resilience under urban rainstorm scenarios. So, why we focus on the rainstorm? We see recently a lot of rainstorm and flooding happens in China. For example, in 2024, in my city, Changsha experienced a very bad flooding. And in Zhengzhou and our capital city, Beijing, also experienced those large flooding events. And those events is more and more frequently seen in large cities. And those heavy rain and urban flooding is affecting traffic and other basic urban functions. For example, the rainstorm impairs drivers' visibility and road safety conditions, cause severe waterlogging on urban roads, resulting some bad effects, for example, the traffic congestion and roadblocks. A large number of vehicles are damaged, people trapped in their vehicles, and hampering the speed of rescue vehicles. So what we need to know in such circumstance, the first thing is we want to know which roads are less resilient and which areas have poor traffic function, and how to identify the weak location in real time. And in this research, we decided to focus on more focus on the vehicle travel mode rather than pedestrian or the, for example, underground traffic mode, because the vehicle in large cities in China is a main traffic tools for people. And we see that because the road got waterlogged or flooded, it causes a systematic traffic failure and people trapped in vehicles. And after the flooding, a large number of waterlogged vehicles caused the heavy burden for the environment. And we see that the existing methods for the road resilience measurement, there are mainly two type of methodologies. The first one is we call it road network resilience, which focuses more on the typology-based measurement that assesses resilience using indicators like connectivity and redundancy by removing the nodes and edges through random or designed attacks. And the second methodology, we call it road traffic resilience. In this measurement, we use functionality-based measurement that evaluates the resilience using dynamic indicators, such as the performance loss during the disasters, recovery speed, and traffic and travel time. I will show you a theoretical diagram later on. So in this background and focus on the vehicle travel mode, we decided to study how to scientifically and effectively evaluate the resilience of urban road networks on the rainstorm and waterlogging scenario, and identify the location with weak traffic resilience capacities so that strategies to enhancing traffic resilience could be further explored. In these slides, you will see that if you are familiar with the literature of resilience, you will find this figure very familiar because it shows how resilience is defined. For example, in our research, we define it as the rainstorm resilience of road refers to the ability of road networks to resist waterlogging, maintain proper traffic functions during heavy rain, and recover quickly. So under this definition, let's look at this theoretical model. The yellow shaded area means the allowable function variation intervals. So any, for example, traffic speed or traffic capacity of roads within this function are allowed, or we say it as the normal scenario. And in this figure, you will see that in T0, we experienced interruption, which could be flooding, earthquake, or any disaster that disturbed the system and caused the traffic function decrease. So we see that in this figure, the function losses, and in the T1 reaches the maximum function loss. And after that, some system might recover and some system might just collapse. So we see that if the system recover, and there is another figure, we call it a recovery rate, which to measure the resilience. So with all those figures, we can define or measure under this definition. But in reality, how we use data and translate those figures into measurable indicators. So we choose a city called Shenzhen. If some of you are not familiar with China, Shenzhen is a very new city, which very close to Hong Kong. So we choose this city as our cases. So as we see that in this figure, the first thing is we need to define which is the allowable interval. And we need to define the disturbed event. So for Hong Kong, we searched the data and found that in 2019, September 17th, there is a heavy rain, which is 45 milliliters within 12 hours. We defined this as the heavy rain events. And in order to compare, we also need to define the normal scenario, which is because the 17th September is a Tuesday. So we need to define or find a day that is also Tuesday or weekday with no rainfall and non-holiday and has no major events. So in that case, we selected the 24th of September as the normal scenario to compare with. And what data set we use? In this research, we use the GPS data of taxis. And in this data, we can extract the license plate, longitude, latitude of the taxis for every 5 seconds. And also we extracted the GPS speed and the directions of the vehicle. So that's the data we have. But because this data has some quality issues, so the first thing is we need to do the quality analysis and do the data cleaning because we need to do the time filtering, spatial filtering, and some drifting data cleaning, etc. And after that, we got the location of each taxi GPS locations with the speed that linked to those dots. So that's the data we use, and then we need to use those data to assess the resilience. The objective one is which road is less resilient. So we need to link those dots with the road segments. So how we do that is we buffer the road with 40 meters, 60 meters, according to the different type of roads, and then match the GPS with our road segments. That's our results, which shows the speed performance. This figure on the bottom left, you can see that is the overall road performance for the whole city as Shenzhen. The yellow buffer area is the allowable, which is, if you remember that this is the normal day without rainfall. And the blue dots or blue line is the 17th September, which has the major rainfall. It's very obvious that as soon as the rain starts, the speed got disturbed. So the traffic function got affected. But the rainstorm warning started later than the system reflects. And the total duration of time is about 6 hours in total. So that's how the whole traffic system perform in Shenzhen. And in the other figures, you can see that we separated the different type of roads as motorways, expressways, main roads, secondary roads, and the local roads. Comparing different type of roads, we found that the motorways and the local roads are affected, has a less duration of affected time. You can see that this time of affection or disturbance is narrow than the expressway or the main roads and the secondary roads. So let's see the figure. Also, we can see that the duration of the disturbance duration shows as what I said. And also, let's look at the resilience loss and the system resilience. You can see that the motorway, the system resilience is 0.9. The total value is 1, so which means 90% of the function maintained. The entire road network maintained 94% of function, but the motorway only maintains around 90%, and the local way performs better, and the secondary road performs as 96% of the function maintained. So that's we categorize the different type of roads, and the other thing is we can calculate for individual road segment and how those segments perform during the flood events or the rainstorm events. If you look at this figure shows the total disturbance duration. and the red means more, the most red ones means those segments has disturbed more than 5.5 hours. You can see that Futian district got most affected and the Nanshan district. And I will show you later on why those lines showed red. And the second figure I want to show you is the system resilience. As I said, if the resilience shows, for example, 0.6, which means during the flood events, the system maintained only 60% of the traffic function. So you can see that a lot of small lines, they have maintained more than 60% or around 60% to 80% functions, which acceptable, I think, because the size of the rainfall might slow down your driving, but the 60% of the traffic function can be maintained. But however, there are some small road segments that only maintained less than 40% or even blocked at all. So that's the method we use to identify which road is less resilient. And the second one is we want to know which area is less resilient. So in terms of the area, we use a grid as the spatial unit. So in this case, we do not exclude those dots or the taxi speed that is outside the road segments. And those is the result we can see for the whole Shenzhen area. And if we look at the individual grid, you can see that some grids shows as this figure on the top left, which means the resilience is not significantly affected because the blue line is the day with flooding, but the orange line is the day as a normal day. So a lot of the grids shows like this, which is not affected by the flooding, but some grids, if we look at the city specifically, those grids, it is 500 meter by 500 meter large. So in China scale, it might be a neighborhood. So a lot of neighborhood shows like those which has longer disturbance duration and has a lot of loss of traffic functions. For example, the grid 2335. And if we map those results on the whole area, it looks like those lots of area got affected longer than 4 hours. But luckily in Shenzhen, large area can maintain more than 60% of the traffic function. Only a small amount of grids shows like here has lost more than 60% of functions. So that's just the preliminary results of our analysis or the assessment of road traffic resilience. To reflect or think what story we can tell from these preliminary results, we can see that as I has already presented, the different type of roads shows different performance. And also if we locate those, you see that the triangle dots, those are the places which is reported as waterlogged area. If we connect those waterlogged area with our assessment of road network, we can see that it's not significantly coincident. Some area has waterlogged, which also lost a lot of traffic functions. but some area is waterlogged, but the function is maintained well. So we can say that there is a spatial heterogeneity there. So that we can explore why this phenomenon exists or happens. And also I want to show you that it's interesting to find that those lines surround the large area. Here, you can see that there's a large blank area, and the roads surround those large blank area seems less resilient than other places. You can see those. And we try to explore why that happens. And we found that all those blank area are the large park or large university or large public space because those parks are gated. So the traffic cannot easily go inside the park. Another example is you can see here. Again, it's a park, but the roads surround those park showed less resilient during the flooding or rainstorm. So we are thinking that during the emergency evacuation, because we have already planned the evacuation route, and normally we use the main road or the expressway as the emergency or rescue ways. But during those kind of hazard, maybe we can open those internal roads to enhance the resilience or to complement the loss of the functions. What next we are going to do is maybe analysis the weak traffic resilience on urban functions such as the surrounding of schools and the hospitals, whether those schools, hospitals, or the infrastructures are affected by those roads with weak resilience functions. So that's all we have done so far, and there are some weakness for this research, but comments and questions are welcomed. Thank you, Antonio.
Oh, thank you, Doctor. Was a very interesting presentation. We have here a question. How do heavy rains affect city roads?
How do heavy rain affect city roads? As I show in my first slides, in China, the heavy rain are very common. Oh, sorry. Can you still see
This
my screen?
question, yeah, this question is more focused on the structural
Focus on, sorry, what?
things. Yeah.
Pardon?
If the research has a structural view, it means how the heavy rains affect the roads in the part about the structure. Huh?
Oh, you mean structure? Do you mean structure of the road, like the connectivity, accessibility, etc.?
In this case, about the structure focus about how was designed a road. Because obviously each road is not equal and have different structural design. Yes. In this scenario, what road is more vulnerability, have less resilience in a heavy rain?
What I understand for this question is we separate different type of the roads. For example, the motorway, main roads, secondary roads. The results actually shows they are differently affected by the rain. And what you mean, the structure of the roads, I don't know whether I understand correctly, is that the connectivity of the roads. That's another type of methodology. As I presented in the very beginning, there are two types of methodologies to measure the resilience. Another way is to use the topographic structure of the road networks. And we presume there's a random attack or there is some specific attack of the flooding. For example, we give the flooded roads or flooded area. So the roads are blocked or the roads are excluded from the road network. So, but in this research I presented today is using the real time of taxi data to express how the resilience performance, but we don't use the assumed attack. Does that?
The sense of the question is about the structural design. Maybe in a scenario with a heavy rain, we
yeah.
have concrete roads. We can have graveler roads.
Yeah.
About obviously, maybe you already take the main idea. Yeah, thank you.
Yeah, that's the main thing I think we need to do next is to evaluate or to look at in detail why those roads are less resilient, whether it's connected to its design. Because you see that, for example, this road, significantly that this is an area with water lodge. So of course, the structural design of this road has problem. We need to improve that. But for other places, for example, here, there's no water lodging, but the traffic affected, the function has lost a lot percentage of the, for example, speed. So we need to think for those area, there's no water lodging, no flooding, but why the traffic speed is affected, whether the wide of the roads, whether the design of the roads is the main cause of the resilience problem.
The
So
main
that's
cause.
what we are going to do next.
Okay. So thank you so much for the presentation.
Okay, thank you.
Yeah, no. And the next presentation, research on the evaluation and improvement strategy of port traffic congestion resilience.
Okay. Thank you, Gordon. Happy to see you again.
Very welcome. Same. Thank you to see you again.
Okay, thank you. Hello, everyone. It's my glad to share my research in this important conference. My topic is the research on the evaluation and improvement strategy of port traffic congestion resilience. My report will follow by 5 aspects, and the first part is the introduction. The increasing annual growth of port cargo throughput and the extreme weather have aggravated port congestion issues. Therefore, how to scientifically assess port congestion and evaluate the effectiveness of the resilience strategies have become an urgent problem to address. Table 1 and 2 summarize selected studies from the past 5 years in port resilience assessment and port simulation, respectively, along with their key contributions. Some studies primarily focus on port performance during different phases of destructive events, while few directly investigate port congestion as the research subject. On the other hand, some proposed mitigation measures lack empirical validation in exciting research. Therefore, our objectives are establish an evaluation framework for port congestion resilience and conduct effectiveness of enhancement strategies. Second part, assessment indicator system. Figure 3 presents the assessment system, which comprises 5 indicators across 2 dimensions, traffic value and time. Figure 4 illustrates the interrelationships between these indicators and their corresponding data sources. The destination calculation formulas and the parameter of each indicator are detailed in Table 3. We adopt a combined subjective and objective weighting approach to assign weights. The subjective method employs the expert scoring method, while the objective weighting is determined through the critic method. Third part, calculation of port traffic congestion index. The AIS data undergoes pre-processing comprising 3 steps: data filtering, denoising, and statistic information matching. The vessel staying events are extracted using the sliding window method with 5 detection features established. Through membership functions, all indicator values are converted into resilience assessment levels, which are subsequently fused using evidence theory to derive the final resilience index. Fourth part, simulation and model construction. The container ship navigation and operation process include 6 phases: anchorage waiting, port entry, berth operation, loading operations, departure operation, and ship departure. Figure 11 and 12 demonstrate the vessel agent creation process in the model, while Figure 13 and 14 illustrate the extreme weather event setting. The model incorporates real-time tidal heights simulated through imported external tidal data, with vessel type detection checkpoints established for ship routine. The berth selection model configuration is presented in Figure 18 and 19. Fifth part, case study. This study conducts a case analysis using AIS data from Qinzhou Port spanning January to June 2021, 213 berthing events and 221 anchorage events were discovered in January. Table 7 displays the calculation results of the 5 indicators across the 6-month period, while Table 8 presents the final combined weighting outcomes. Table 9 shows the confidence levels for different indicators, and the resilience index is shown in Table 10. From January to June, the index January exhibited an upward trend, with January recording the lowest value at 0.26 and March reaching the peak at 0.65. The month with the highest confidence level for good, average, and fragile resilience was March, February, and January, respectively. To accurately simulate the operational dynamics of Qinzhou Port, the model first processes tidal variation data, then calculates tidal access window for vessels by integrating the designed water depths of both east and west channel with the specific draft requirements. The resulting tidal clearance calculation are presented in Table 11 and 12. Qinzhou Port has 3 berths for 5 to 7,000 ton vessels and 10 berths for 20 to 200,000 ton ships. The input data format for the model is specified in Table 13, while statistical time nodes for vessels are illustrated in Figure 24. The final model's input data format is presented in Table 14, while the overall operational performance and indicator variation are illustrated in Figure 25 and 26 respectively. We propose two distinct resilience enhancement strategy. Strategy 1 deploys vessel arrival peaks during high traffic period. And strategy 2 implements back-to-back birthing operation, effectively minimizing birth idle time. The picture shows the simulation results for the initial state and the implementation of strategy 1 and 2. Then we draw the conclusion. First point, the overall operation effect of first strategy is better than the second strategy. Second point, first strategy may potentially delay port entry for vessel carrying time-sensitive cargo, which could lead to shipper dissatisfaction. Third point, second strategy is suitable for ports with a high frequency of ship arrival and shortage of berth resources. Okay, that's all. Thanks for listening.
Thank you. Thank you for your presentation. We have here a question about the good presentation. How is combined the physiologic and evidence reasoning for improve the index of this method? In simple words, how can be improved this method for more exactly values in the index when is making the calculation?
Okay. First, I use the sliding window method to mine the ship state events. That's the foundation. It's also the data input. And second, we use the fuse evidence reasoning. Select the membership function of triangular and trapeze combination. And last, using the evidence theory to achieve the fusion of multiple port congestion resilience assessment indicator. That's what we use the method in these cases.
Thank you. Thank you for the good presentation in this event. Then, as we close this chapter of ECI Winter Edition, we are very glad to receive these great presentations, and the people that are synchronizing now the live stream via YouTube are invited for the next edition. Thank you for all the presenters for the very interesting presentation. Bye bye and good day.
Goodbye. Got it.
Goodbye.